Great. So now we're going to talk a little bit about obstacle avoidance. And this you should, if you haven't watched it already, check out the dot product review or go open up the Wikipedia article for it or something, and just briefly review the dot product because we're going to be using a healthy use of it in this discussion. And so, what is obstacle avoidance, and how is this different than fleeing something? So, I'm going to use completely unlicensed, use of Star Wars in this slide deck, which I 100% approve of, so I left it in. In general, what we want to do is we want obstacle avoidance is effectively just want to avoid obstacles. So if you have an agent and an environment with a bunch of different things, and you want them to be able to navigate that environment without getting stuck in a corner, or if you've ever seen a Roomba get stuck on something, you want to kind of avoid that. And so obstacle avoidance gives our agent the behavior and ability to maneuver around in their environment without hitting obstacles, or at least trying to. So the difference between flee is always the case, right? So we somehow have omniscient knowledge of your environment, and you can always sort of move in the direction opposite, away from something. But obstacle avoidance will take action only when there is an obstacle impeding the progress. So, for example, how do you calculate line of sight here? How do you ensure, technically one agent can't see the other agent, and obstacles would impede that. And so even though our game or our simulation can know where everything is, otherwise it wouldn't be able to render it and calculate what's going on, but our agents don't necessarily want to have all of that information. So how do we do that? And obstacle avoidance is actually both a way to know when there's obstacles in your way, so that you can avoid them, but also when there's obstacles in your way so that you know not to tell an agent that there's, say, an enemy on the other side of a given obstacle if they can't see that enemy. So, for example, where the obstacle avoidance, in this case, if you have like a, Star Destroyer and a TIE Fighter, right? They're moving together, and there's no real concern with obstacle avoidance because the TIE Fighter is not moving at the destroyer, but at the same time, if it's getting a bit too close, it's going to incur a flee, force, and that's going to kind of nudge it away from the Star Destroyer. And so again, the key here isn't to create this sort of complicated logic structure. If you create sufficient number of these forces that sort of interact with each other within an environment with other agents with these forces, it all kind of creates this sort of dynamic environment, and emergent behavior will emerge out of that. The best example I like to give on this is thinking about birds flying in formation. Each bird doesn't really have to think about the formation of the entire group. They just have to ensure a certain separation distance between them and their neighbors in a particular way. And if they do that, then they produce a very particular kind of like triangle-like or kind of a V-like configuration, right? So the number of rules are really simple, but the behavior, the emergent behavior that comes out of those very simple rules can be really complex and interesting. In fact, the behavior of ants and how they can produce what is a very, very intelligent organization of ants, but with individual ants actually having very little intelligence or capability on their own, is something that there's still an active point of research. So in this case, the TIE Fighter is actually going to hit the destroyer. Obviously, if you have a sufficiently strong flee force in effect, but say that's not strong enough to avoid it once you get too close, and so obstacle avoidance will allow you to change direction well before your flee force even needs to kick in. So how do we choose obstacles? Well, we talked a little bit about the dot product previously in the last lecture, and how you can use the dot product to determine on which side of the agent things are and whether or not they are behind or in front of. So say we look at the stormtrooper in this case is technically behind. So in our little world, things behind you can't see, which makes sense. Most of our field of views is not more than 180 degrees, and so if there's somebody behind you, I know that sometimes you can somehow detect that with other senses, but in our little simulation, we can't see things that are behind us. When we consider Leia in this case, she's too far to the right. There's no way we're going to bump into her based on the direction that we're pointing. Same thing with R2-D2, but clearly C-3PO as usual is in our way. So this is sort of how you can use dot products actually to determine left or right, how far, right, because we can determine the angles. That's one way to think about it, and whether or not they're behind or in front of us based on the if it's positive or negative. Yeah, so in this case, again, like we have the TIE fighter, we can kind of see, okay, we're going to be going in a particular direction. We need to avoid these planets that are clearly in our path, that are impeding our path. There's a really good likelihood of us hitting them, whereas the Death Star is not going, there's no chance that we're going to hit the Death Star because it's to the left and outside of our sort of thing. So how do we detect objects in our path? Well, we need a simple way to detect collisions in our path, and we need to have that is sort of that works regardless of rotation. So you can probably think this is what we want. This is what bounding circles are particularly good at. And so if this would work for 2D in circles, we could do it in 3D with spheres. And so if we just sort of draw a sphere or a circle around each one of the objects in the scene, and now we can kind of consider each one of them related to our agent. And so the thing is, right, if we've already collided with the object in this scenario, it's a little bit too late. We need to detect the collision before that. So what's a potential way to do that? Well, we can take our sphere, we can take our circle and project it out in front of us, or move it out in front of us. Now the problem with this, well, so say we do this, and this is kind of one way to do it, is we sort of check a collision in front of us, and so on. But in that way we can kind of, well, if we're moving slower, we maybe put it out a little bit less in front of us. If we're moving faster, we put it out farther out, because at each time step we're kind of checking, okay, the next time step will we be hitting. And we can even do this farther and farther out. We can kind of project this multiple times. There's actually a pretty popular technique called ray marching that uses a similar kind of approach to this, where it kind of creates a sphere and kind of grows it until it hits something, and then kind of keeps on growing it, and that way determining kind of a path. But that's not what we're going to do here. The problem with this issue, though, however, so while this does work pretty well, we can determine in this scenario that we've hit this future object that we're going to hit. But there is that concern of, well, what if our agent was just slightly to the right, and the sphere would have overshot that, and we would have missed that collision, and then we were going to hit it next time. And so this isn't really take into consideration all the objects in front of us. It's not really great. You can do that ray marching or kind of ray casting approach, but you can already kind of see from this, like, what if instead of a sphere, right, we're able to sort of shoot out a ray and see everything that kind of collides with that, or if we could sort of look at anything in front of us, how can we create this sort of more like a volume projection of the sphere? Because a circle might not be good enough. And so how do we do this kind of with the bottom example, where we take that sphere and we sort of extend it out? And so Reynolds has a really good answer for this. And so the Reynolds test for non-intersection, the assumption is that all the objects are spherical in nature. And the way we do this is we localize the center of each obstacle. So we figure out where the centers are. We then project that center down to a particular plane, to a side up plane. So if we're pointing this way our side up plane would be here, which you'll see kind of why that is in a minute. And then we determine the distance from that point, from that projected point to our point, to our origin. And in a way, it's kind of like, imagine, here I can actually have a little, so imagine this is our side up plane. Oh, it keeps on getting rid of it. And that this is our object. This is our bounding object, this circle here. And so if I were to basically rip a hole, which I'm not going to be able to do very well here, here we go. So now I've ripped a hole in my little thing. So this is like our, say my pickle Rick is my object, and this is basically the thing, right? So it's in a way kind of like looking through the hole, and I can see, okay, if I project through the hole and I can see what's in that way, because what happens is if I take an object and I project it down onto my plane, then I can measure the distance between me and the center of that object on this plane. And you can kind of imagine that's almost like taking a cylinder and kind of extending it out from here. So anything that's inside of that cylinder, I'm colliding with. It's very similar to the bounding sphere algorithm we talked about before in the collision, but instead of doing it with kind of an arbitrary point in space, we're taking that point, squishing it down to our plane, and then determining whether or not it's in that cylinder. So kind of here's an example of that, right? In this case, we have kind of this ambiguous thing. We're pointing up, so the triangle, we're pointing up. This is our right vector, and we take the point and we project it down onto our right vector. And if you recall from our last lecture about dot products, to do that, you can use just the dot product to project down that vector from the point, the center of that other object to ourselves, create that, and then squish it down to the distance between that and where we are. And then it's quite simple to go from that. Now we have this sort of flattened projection, and we can determine if we're colliding or not. So this is just, again, to review, to get this value, what we would do is we would get that vector and we would project it down onto our right vector. Now, our right vector is a unit vector. It's a normalized vector, and this vector is not normalized. It's going to be some wacky doodle number. So actually just taking the dot product in this case will give us the magnitude, that distance. Because if you recall in the last lecture, we talked about dot products to get the projection, right? What happens here is, if you think about that angle between V2C and the right, there's an angle there, and the dot product is going to be equal to the magnitude of the right vector and the magnitude of the V2C vector times the cosine of theta, right? We know that. But cosine of theta in this case is the magnitude of the right vector. It's that bottom part of the triangle divided by the hypotenuse, by the magnitude of V2OC. So if we want to get that magnitude, the cosine is going to be that value, that red line divided by V2OC. So all I have to do is take the magnitude of V2C, move it over to the other side of the equation. So it's basically going to be the dot product times the magnitude of V2C divided by the magnitude of right, which is just 1 because it's a normalized vector, times the magnitude of V2C. And the V2Cs basically cancel each other out. And so what we're left with is that magnitude, that projection is just equal to the dot product, which is pretty cool. So now all we have to do is we take a look at that value and we compare it. Now it's just a bounding sphere or bounding circle comparison, right? If our sphere, if our radius plus the radius of the other object if that is less than the distance, then there's no collision. It doesn't exist in that cylinder. If there is, then we're overlapping, and that object exists in that sort of volume. So in that case, right, you know, it's like saying, okay, here, it's almost like looking through, if I do that, it's almost like here's my object, and as I get closer, now it's in here. That's kind of what we're doing. So, cool. Now what about multiple collisions? In this case, we can kind of see how do we determine if there's multiple collisions. And there's a couple of ways to deal with this. But generally speaking, well, a couple of ways. In the context of this algorithm, there's one way to deal with this. And the first thing we do is we want to filter out objects that are behind us. So to do that, we take the dot product of the V2C and we do the dot product with our forward vector. If it's positive, then it's in front of us. If it's negative, then it's going to be behind us. And to do multiple collisions, all we have to do is we have to basically do that projection test for each one of them. In fact, you could, in theory, combine them if you want, but it's easy enough to just kind of do this. And another thing that you can do is, if you want to only worry about the collision in front of you, about the obstacle in front of you, you can use the dot product to basically project that V2C vector onto our forward vector, and now you can determine how far forward an object is, and so you can effectively check collisions in order of how far away they are from us. And that kind of ordering, by the way, is particularly useful for spatial organization of your scene, and if you're trying to do slightly more complicated things. So how do we implement this stuff? So we can ignore anything behind us. We can ignore anything that's too far to the left or to the right, or any objects that are too far ahead. So now we assume we've done all that, and if now we realize, oh wait, there's an object in our path, then we must sort of steer. We must apply a steering force to avoid it. So the way that we calculate the steering force is basically by negating the lateral side-up projection of the optical's center. So that means we want to steer based on the dot product between the vector and the right vector, right? So if the dot product is positive, we want to, that means that the object is on our right, so we want to go left. If the dot product is negative, then we want to, turn to the left because it's on our right. So it's very easy to know using that projection sort of on which side of us is the object. And so you can kind of see here if we've got an object and it's on the right, then we want to go to the left, and we just create a perpendicular force to our forward vector. And if you guys remember, if you've ever taken like physics, you can probably remember if you have a object that is moving in a circular motion, the force on that object, there's always a force. There's no such thing as a centrifugal motion without a force. And in a centrifugal motion, the force is always pointing inwards at the center, at the pivot around which it's moving. And so applying a perpendicular force to your forward vector will make your object basically turn in a centrifugal, in a kind of circular fashion. And yeah, you can play with the velocity, and you can scale it to the maximum speed and all the other stuff that we've talked about. And this is just another force that you can apply to your object. And so in this case, we just would create a new function called the avoid obstacle method. It would use the Reynolds test for non-intersection. It will return a vector 3, just like all of our other steering forces. And another thing you kind of might want to add to your implementations is, what's your safe distance? Maybe you want to create, again, like we talked about, a kind of like scaling weight to the steering force, so you want to avoid things that are far away less than you want to avoid things that are close. And also maybe bigger things are scarier and you want to apply stronger rotations versus smaller things. So something small, you want to just slightly avoid it and keep your distance. Whereas when something's big, you want to avoid it more aggressively. So yeah, there's a lot of little kind of capabilities and pieces that we can play with. When you implement this, there's a few things to kind of keep in mind. The scripts are really helpful. So creating a helper script to hold the position and the radius of an obstacle can be really helpful because that's how you can access those things in other scripts. The child class, can create and hold on to these kind of base values, so that way you can differentiate these things based on the agent. So say a zombie wants to avoid fire with a bigger radius than, say, a human would, right? Humans don't want to catch on fire either, but they have a lesser aversion to such things. And then now we can implement the obstacle avoidance method in the vehicle and kind of the top level class. And so that way all of the children benefit from that behavior without you having to code it explicitly for each one. So obstacle avoidance is not a perfect algorithm. This is not pathfinding. Pathfinding as would be implemented with the Dijkstra's algorithm or A-star or potentially other ways. It will give you much more accurate and better ways to kind of map a path from one point to another point. That's not what we're talking about here. Right now we're talking about just sort of a general set of forces that will give you emergent behaviors. So this is not perfect. You're going to have wobbliness, which is what you could call resonance, when things are changing rapidly and this is changing, so this is affecting that, and then it changes and it affects it back. You will have situations where they get into kind of a loop and kind of build off of each other, or resonate is the name for that behavior. So keep in mind that that this algorithm is only as good as sort of the constraints and the environment that it's placed in. So for example, below, you'll have a situation where an object doesn't know which way to steer because they're both both these objects are in its path, and it doesn't know what to do because one is on the right and one is on the left, and it's going to apply forces in both directions maybe, and then just keep going straight and hit both of them. And that's not the intention. So you do have to kind of consider the limitations, right? In this case, for example, what you could do, and you can say, okay, hey, instead of having each object go into the force and apply a new force, what you could say is calculate all of the objects we could potentially collide with, right? Then draw a new bounding sphere around all of them, and then make a decision based on that. And that would then allow you to treat these as two objects, which to us, to somebody looking at this, you would say, well, you have to choose left or right, right? Well, your agent doesn't know that, so you need to kind of actually give it that behavior. And one way to do it is to consolidate all objects you could potentially collide with in a situation where you have a density like this. In fact, you can get really deep here and you can say, well, if objects that we're potentially going to collide with are sufficiently close where there's no way between them for our agent, so you do a kind of a second collision test between these two objects and say how much space there is between, and there is not enough space for us to get through. If that's the case, then what we can do is we can say, okay, well, let's treat that as one object instead of two. So there's a lot of kind of very subtlety in how you do actually implement this stuff. Let's talk about navigating multiple obstacles, which I kind of talked a little bit about already. But in this case, we can kind of treat the situation like, well, you've got these objects that they're in front of us, but some of them are too far away to even care about. A couple of things are behind us, so we don't really care because we're going in a different direction. There's no chance we'll ever hit it. But in this case, we've got a few objects that are in our path, but some of them are more pressing than others. And so what we could do is we could kind of steer to deal with the most threatening one, or we can kind of steer in a way that responds to all the threats related to their distance. So we kind of weight the different kind of concerns, as we've talked a little bit about this already. So another thing, as I mentioned this before, an alternative approach too is, in this case, you can kind of look at these three objects and say, well, you know what, I don't really want to weight them, because what that's going to do is one of them is going to give me a force this way, and the other ones are going to give me a force this way, and the other one's going to give me not much of a force. And so I'm going to kind of end up in still potentially hitting one of them, because one of them is telling me to go left and the other one's telling me to go right. Maybe less, but still there's a good chance I might hit one. So what you can do here, again, is you can project all those objects onto your plane, and say, oh, there's actually not enough distance between all these three objects for us to maneuver through. So let's treat this as one object and go in the right direction only, and only have one force. So not only can you, basically, there's three options. One is deal with only one object, the one that's most scary and most kind of pressing. Two, apply to each one with kind of maybe a varied weighting to kind of reduce the importance of the ones that are farther away versus the ones that are closer. But a third option is to consolidate objects in a way that is, then you only have one steering force, and you have to decide which one is the most important one. Cool, so let's talk a little bit about the assignment. I know my lectures are a bit late, but hopefully you've had the slides already, and I've extended the deadline for the exercise a little bit as well in response. So actually read the Reynolds paper, and feel free to skip some of the sections that are not relevant, but the most important ones is the obstacle avoidance, wander, and separation, and combining behavior sections. And then exercise 12 is write the obstacle avoidance capability and implement that in your humans versus zombies project. So no new exercise project or anything like that. Just work on it inside of your humans versus zombies project. And both the humans and the zombies are expected to avoid obstacles of some kind in the scene. Use just basic game objects during testing. Either randomly possession them or put them there yourself, doesn't really matter, but the algorithm should be, not hard-coded. This is very helpful, like debug lines, I'm sure you guys have already sort of discovered, are very, very helpful, especially in determining what's going on with like real-time systems. And again, this system, Reynolds, is not perfect. I've given you a couple of options of how to make it a little bit better, but keep in mind that it's still not going to be perfect. And so creating some helper scripts determining collisions and doing the stuff a little bit more modular than before might be really helpful. In this case, the submission is just for scripts. You don't need to provide a whole thing, just the scripts. That's it. That's it for obstacle avoidance. And excited to see what you guys do.